How are sound waves absorbed and reflected on different materials? My name is Coen Klingbeil. My research supervisor was Mrs. Ford. My English supervisor was Mrs. Ryan, and I'm from St. Paul School, Westerville, Ohio. How did I get the idea for this project? I wondered why sound is heard different in different places. I wondered if differently designed materials could affect how sound gets rebounded off of them. I noticed that music recording places have specific materials on the wall, and I did not know why. Where did I get my experimental design from? I found the general idea of the experiment on Science Buddies. I then modified the experiment to answer the question that I wanted to answer, which was how sound waves absorbed and reflected on materials. I originally created a rectangular box out of wood with a slot in the middle where I could slide the material into, and the sound would go through the box and get absorbed or reflected by the material in the middle, and eventually reach the sound meter on the other side of the box. I had to revise my experiment due to inconsistent decibel readings. So I switched to covering the speaker with the material with a decibel reader on the other side of the material. Background information. Sound is vibrations that travel through air or a material that can be heard. As the sound wave is spread further apart, meaning it gets further away from its source, the sound wave's energy begins to decrease. Intensity, tone, and pitch cause the differences between sound. The amount of energy a sound has over an area is called intensity. When the intensity is lower, it is referred to as soft, and when it is higher, it is referred to as loud. The measure of energy is amplitude. The higher the wavelength, or the louder or stronger the wavelength is, the more energy the sound wave has. If there is a high amplitude, then there is high intensity, and the intensity is measured in decibels. Sound waves are absorbed into material and reflected off a material at different frequencies. If a material is dense, it will reflect sound waves the best, because dense materials are strong obstacles against sound waves, and there is less space in between the molecules of the material. Reflection examples include gypsum board, wood, concrete, brick, and tile. If a material is porous, meaning it has many holes, it will absorb sound waves the best, because the space in a porous material allows waves to pass through. In a porous material, there is more space in between the molecules, so the sound waves have to move around in the material space, causing the waves to be quieter or get absorbed. Absorption examples include carpet, foam, mineral wool, and fiberglass. In the bottom right, there's a diagram showing absorption and reflection on different surfaces. So, my hypothesis. If sound waves are played through different materials such as foam, wood, and drywall, then the sound waves played through the foam will be absorbed the best and reflected the least. My null hypothesis. If sound waves are played through different materials such as foam, wood, and drywall, then the sound waves played through the sound waves will be absorbed and reflected at the same rate. My experimental procedure. Number 1. Gather all materials in a very quiet room. Number 2. Open up logbook and create a data table. 3. Create barriers built out of each of the material, meaning cut each material to the same size. Number 4. Pre-record a sound played on a piano, recorded on a phone, in which it will be used consistently throughout the experiment. The piano was one note recorded on a phone, not a musical piece. Number 5. Put a sound level meter on one side of the material barrier and pre-record the sound played on a device on the other. Here's the sound level meter, and here's the speaker used for the experiment that was Bluetoothed from a phone. So play the recorded sound and write down the received data on a sound level meter. Repeat step 6 at a minimum of 5 times. Number 8. Switch out the most recently used material barrier and put a different material barrier in place of the recently used one. Number 9. Repeat steps 6 and 7 and 10. Continue repeating steps 6, 7, 8, and 9 in that order as many times as it takes to get a sufficient amount of data, at least 5 to 10 times. Here are some examples of materials. This is foam A, this is foam B, and here is tile. I used 8 materials in all, and some of them I hoped that you could image in your head. I could not get all of them here right now. So this graph shows the mean, median, and mode of each material. On the left side shows the decibel readings, and on the bottom each material. You can kind of see you can see the mean, median, and mode. You can kind of see how consistent they are through the readings, and how some are higher and lower than others, as some absorb and reflect at different rates. This graph shows the change of the materials, meaning it's the difference between the highest and lowest reading. It's the decibel range in between them. So if there's a lower change, then that means there's more consistency because there's less space for the decibels, all the decibel readings to lie in. You can see that tile, drywall, and wood have the most consistency because there's the least change in the most consistency, averaging at about 9.5 decibel. So here are 4 graphs of the materials I used. You can kind of see how some are more consistent than others, and they show that where the decibel readings lie. And it's hard to kind of tell where how some are higher than others, but once you average them out, again back to the mean, median, and mode graph, you can kind of see a lot more of how they look and how they're different from each other. So no materials, obviously, well, it's the highest. The cloth is a little lower, tiles a lot lower, and aluminum is near tile. Here are 4 more graphs, same thing. Foam A and Foam B were close to the no material because they have the most absorption and they're the most porous material. And wood and drywall are good at reflecting and have the most consistency. So my conclusions. My hypothesis was supported and my null hypothesis was not. My further findings include that some materials are more consistent than others. When there is no material blocking a sound source, there is less consistency, and this is confirmed as the less dense materials such as Foam A and Foam B were not very consistent, along with when there was no material blocking the sound source. So again, as you saw, Foam A and Foam B were not very consistent at all, but that's because they were more porous and there was more variables impacting how the sound was recorded on the decibel reader. Also another finding is that all the conditions surrounding the place where the sound comes out of are important and impact how the sound gets reflected and absorbed, like I said. So my areas include that sound was likely leaked out of gaps between the material and the speaker, and that the materials varied slightly in size. So what's next? I would like to create a more consistent experimental environment with fewer variables impacting the test. I'm very interested in performing and recording music, so I think I'd be able to use what I've learned in this experiment to be in the best surroundings when I am performing music. Liking music is also one of the main reasons I did this experiment, along with being interested in physics in general and being interested in the way sound occurs. This project was very interesting and I'm glad I chose to do it. So thank you for listening to my presentation and judging my project. I have learned the value of breaking up a big project into smaller pieces, how to write and follow a procedure, how to create a loom presentation, that science experiments take a lot of trial and error, as in my experiment, I had to try many different methods to get my final result, how to record decibels with a decibel reader, and how to organize data on a spreadsheet and in graphs. Thank you, and bye.